Okay, so today we are going to talk about KSP values. So we'll dive into the actual value later. It's like an equilibrium term, but a little more specific when we talk about solubility. So solution equilibrium. This is just what is formed when a solution is saturated, because you're going to have the rate of dissolving equaling the rate of precipitating. So as fast as we can make our ions, that's the same rate as much as we can put those ions back together. So an example of a solution equilibrium would be taking our solid salt NaCl, double arrows, and showing it dissociate into its two ions, giving those states of matter aqueous because we are dissolving it in water. So dissociation of electrolytes, I wanted to show you a bunch of kind of examples. So our electrolytes, those are going to be our ionic compounds, metals and nonmetals. So I'm just representing them with generic M and A. M for metal, A for nonmetal. And so our metals are going to be what form our positives, nonmetals will form our negatives. But when we start having compounds that have like M2A, that means when it dissociates, you're going to get two metal ions for every one nonmetal. Or M2A3, you'll get two metals, three nonmetals. This one compound dissociates into 5 ions. So I just want to make aware of when we have our chemical formulas, understanding that those subscripts actually end up being coefficients for the ions. Any question about that? Cool. So we're going to kind of bring back the idea of a mass action expression. That is this guy here. So that's when we write our products over reactants. And so we just need to remember these mass action expressions because we're going to use this to convey how soluble a solute actually is. And so reminding ourselves, we're writing products over reactants. If we have a coefficient that goes as the power in the mass action expression. And yeah, any questions there? Okay, this should just be review. Now, thinking about what this ratio is. This is the ratio of the ions over the ratio of the solid. If you think, what do you think represents a higher solubility? A big K or a little K? A big K, because the higher the K, the higher the top portion of this ratio. That would make sense. The more soluble, the more ions you form, higher ion concentration, we increase the top part of the ratio, making a bigger number. So the blanks here is that we have for the higher the K2, the higher the solubility. Now, unfortunately, not everything is as great as dissolving as sodium chloride. So we need to talk about the solubility product constant. This is KSP. So some salts really like each other. The ions really want to hang out together. So it takes a lot of solvent to start to actually break them apart. And so the only concentrations that you can start to form somewhat of an equilibrium, otherwise it'd be forced too much one way, is at low concentrations. And so because the concentration is so small, that if we were to calculate a KEQ, like a mass action equation here, so what it's saying here, I'm going to write another generic one to represent this. If this top part, ions, if this concentration is really low, what do you think KEQ will start to approach? 0, exactly. So I don't know if I fixed that, but it would equal 0. So what we do instead, because this is of absolute no use to us, we can't compare salts that are just a little bit soluble because they all would look like 0. So what we end up doing is just dropping out the concentration of the solid and looking at just the concentration of the ions. And we call this KSP. So we use this to compare relative solubilities of really insoluble salts. So what these 3 asterisks here are for is that the concentration of undissolved solid is ignored. So now our equations get even easier. Instead of writing a whole mass action where you have products over reactants, we just set it up as products. So the products of this are M plus, and then we'd be multiplying that by A minus. So that is how you write a KSP. Second one here with real examples, you would write that your KSP is equal to Ag plus 1 times the concentration of Cl minus 1. Last one here, the only thing you have to consider different is the coefficient in front of Li. So KSP is equal to Li plus 1 to the 2nd power multiplied by CO3 minus 2. Any questions on writing KSP equations? Not too bad. So again, instead of having a ratio, now it just makes sense that the higher the concentrations of our ions means the higher the KSP. You guys see how they're directly related? If you were to increase the concentrations on this side, you would increase the value of KSP on this side. So the more soluble you are, the more ions you form, the larger the KSP. Any questions before we move away from chapter 10.4? All right. So we are not going to finish 10.5. We'll finish that on Wednesday, but we are going to begin talking about colligative properties. And so the definition of a colligative property is just their physical properties of a solution that don't depend on the identity, but on the concentration of solutes in a given amount of solvent. So the reason why we're going to do a road salt inquiry is because that has very much to do with colligative properties. So you guys have heard we salt the roads during winter. It helps keep the freezing point low enough where the ice doesn't actually form. So if we just had normal water, pure water here, when it freezes, it forms this nice little block, very crystalline structure. Now, if we mix and dissolve salt into that water, the salt just kind of gets in the way and starts kind of breaking down its ability to form a nice structure until eventually water is like, no, get the heck out of here. Let me form my ice. And so what ends up happening is it just lowers the temperature that water is able to do so at because of it preventing this physical change from happening. So what you're going to be doing in your project is looking at what salts do this the best. Now, electrolytes versus non-electrolytes, this has to do with talking about how many ions they can form. So as we could assume electrolytes, these are going to be our ionic compounds. We'll talk about acids. They are actually kind of non-metal electrolytes in a way, but they're a very special case. So we'll talk about acids next chapter. But with our ionic compounds, they'll dissolve and conduct because they're freely moving what? Ions. So ions in solution. You guys should know that those two go together. And so what we say is they ionize 100%. And so it looks like a decomposition reaction in the sense where if you look at this example here, we have a one-sided arrow because all of the sodium chloride in this case will fully dissociate into its ions. We call this a dissociation. So we give it another special term. It's not decomposition, but actually dissociation when a solid ionic compound forms its ions. And so we call this a physical change, not a chemical one, because the identities of these things aren't changing, it's just changing forms. And so looking at this, we can read our first example is that 1 mole of NaCl, sodium chloride, will dissolve to form 1 mole of sodium ions and 1 mole of chloride ions, so 2 moles of ions total. So 1 mole of solid gives us 3 ions. Next example here, we can see that we have 1 mole of aluminum nitrate, and that dissolves to form 1 mole of the aluminum 3+ ions and 3 moles of the nitrate ions. So it'll give us 4 moles in total. The reason why it's important to understand how many moles we're getting, because this will actually affect which will have the higher or lower boiling and freezing points. So we'll talk about freezing point depression and boiling point elevation in a second here. First, we gotta just talk through how non-electrolytes affect colligative properties. Well, we know they form what type of bonds? Covalent. So our non-electrolytes have covalent bonding. They don't dissolve when they enter water. Or sorry, don't dissolve into ions. They don't form their charges. They do happen to dissolve pretty well, but they're not going to ionize. If we don't have ions, we can't conduct electricity. So this is something to think about for freezing point depression, which is the freezing point of water will decrease as we add solute. So road salt example. And I think I forgot to change this on your guys' sheets before I printed them, but it should say boiling point elevation, not depression. My apologies. So if we change that to say elevation, as you guys would probably assume, the boiling point of water increases as solute is added. This is why people add salt to their water when they make noodles, because if we can get it to a higher temp that it's boiling at, the faster the noodles will cook. It does also taste better. So this next part is we are going to practice. Oh, I guess I should probably show you this example here. So this is just a visual representation of how it works to increase the boiling point. If it's just the solvent, they have no problem moving past each other, getting into the gas vapor. But if you have a bunch of solute in there blocking them from being able to move and escape, you're gonna have lower pressure, less of them are gonna be able to get out. Your boiling point will be at a higher temp. All right, so we're gonna go through some example questions here. What I want to summarize for you guys, when you add solute, if we think of freezing point being on a scale with the boiling point or something, when you add solute, it expands them outward. So freezing point gets lowered, boiling point gets higher. So it makes the boundaries expand outwards when you add solute. Okay. The first question here asks which of the following solutions will boil at the highest temperature. So we need to figure out which one has the most or least solute. What will give us the highest temperature? The biggest concentration, which is D. So we are looking for the highest concentration because the more solute, the higher the new boiling point. If you were to look, the largest concentration will be D. All that's changing is how much water it's dissolved in. Being dissolved in the least amount of water means it's the highest concentration. What about if we want it to boil at the lowest temperature? A, we're looking at the lowest concentration. Therefore, it won't affect the boiling point very much. So that would be A, lowest concentration. What if I ask about freezing now? We want it to freeze at the lowest. Are we looking for a high or low concentration? High. So whatever direction, so you think of freezing being cold, the colder you want to get, the higher the concentration. If you're boiling, the hotter you want to get, the higher the concentration. So a higher concentration will lead to a lower freezing point. So what letter would that be? D again. Now, if we're looking at freezing at the highest temperature, which will affect it the least? A. Again, looking for that lowest concentration, which remained at A. Any questions on these? Okay. Now, let's talk about it with the number of ions we have. So number 5 says, which of the following solutions will boil at the highest temp? So now we're going to relate, instead of concentration, number of moles of ions. So do you think we want a high number of ions to affect it or low? We want high. Just how we want the highest concentration, we want the highest number of moles. So looking A through D, how many particles will we have in one? Or sorry, A. It would just dissolve maybe, but it would just kind of stay as is, right? How many ions do we have for B? 2. How about for C? D, 4. So we get 1 and 1 for KBr. We get 1 magnesium, 2 fluorines, 1 aluminum, 3 chlorines, which if we total these, you'll see that D has the most number of ions. So that would be our best option to get the highest temperature for it to boil at. What about the opposite then? What would we want to use to boil at the lowest? A. Because we want lowest number of particles. 7. How about freeze at the lowest? We're looking for high or low number of ions. High again, that gives us D. What about 8? A, awesome. All right, so this is all I have for lecture. You guys have 2 sheets